Hi, my name is Akash Bhatt, and this is my presentation on Lab 5 regarding Faraday's law. In this lab, we modeled a current-inducing time-varying magnetic field by performing an experiment with an aluminum foil tube and a magnet. We dropped the magnet through the tube to see the effect of Lenz's law, as a current was induced in the foil by the magnet. The magnet creates an external magnetic field, and this field therefore induces a current in the foil tube. For the theoretical portion of the lab, we then recreated this model in GlowScript. In doing this lab, we used 4 physics concepts that we have learned this year, the first of which is Faraday's law. This law relates the induced voltage and the rate of change of magnetic flux. Basically, a changing magnetic field results in a change in magnetic flux, and this change in flux creates an EMF. Using Ohm's law, V equals IR, we can use this EMF to determine the current at that object. This current opposes the change in flux at that location. The second concept we used was the Biot-Savart law, which explains how a bar magnet can produce a magnetic field, and that equation to find the magnetic field is listed to the right. We also used Lenz's law, which claims that a magnetic field from an induced current will always oppose the change in flux. So in our case, it'll oppose the magnet's magnetic field. The fourth concept that we used was Newton's laws. The first one, force equals mass times acceleration. And the second one is that for every action there is an equal and opposite reaction, which is Newton's third law. To complete this experiment, here are the steps that we followed. First, we used the magnetometer already on our phones from Lab 3 to determine magnetic north on the magnet. We marked this location so we can use it later. Then we recorded with our phones the magnet dropping through a tube of foil. We then scrubbed through this video to see exactly where the magnet enters and where it falls out of the aluminum tube. And we calculated that time and completed this 5 times and then found the average of how long it took for the magnet to fall through. Here are the results from our experiment. After each of the 5 trials were completed, we calculated an average to see how long it took for the magnet to fall out of the tube. To model this computationally, we first inputted the dimensions of the tube that I used to make the results of our computational model specific to my tube. Then we calculated the field due to the bar magnet, and then with that information calculated the magnetic flux. Using this flux, we calculated the current in the ring using Ohm's law of V equals IR. Here is a picture of the magnet as it falls through the aluminum tube in the computational model. The blue ring represents the clockwise current, while the red ring represents the counterclockwise current. This image is shown here on the left. On the right of the screen is an image of the graph of velocity versus time as the magnet falls through the tube. As you can see, for a portion of time, the velocity is constant. This is because at this moment in time there is no net force acting on the magnet as the forces in play cancel out. To better understand this simulation, we can draw some conclusions. The blue ring represents the clockwise, while the red ring represents that which is counterclockwise. Flipping the magnet around will flip the currents, however the motion of the magnet as it falls through the tube will remain the same. Experimentally, we found the average time taken for the magnet to fall through the tube to be 1.3 seconds, while computationally this value was smaller at 1.13 seconds. The computational model, however, can be made better if we were to account for air resistance that the magnet experiences as it falls through the tube. The graph shows for a portion of time that there is no net force as both forces cancel each other out and the velocity is constant. This is because the net force is 0 at this point in time. To conclude this lab, let's go into some hypotheticals. What if the resistivity of the conductor was reduced as close as possible to 0? How would the dynamics of the falling magnet change? Well, if the resistivity decreases, the induced current will increase as V equals IR. Therefore, the time that it takes for the magnet to fall will increase. And if the resistivity was 0, the magnet would stop falling. This, however, is not physically possible. If holes or slots were cut into the tube, this would affect the ring current in my model because there would be less rings and the induced current would decrease. Therefore, the magnet would fall faster. Thank you for watching. This has been my presentation on Lab 5 regarding Faraday's law.